Okay, so I want to return to conservation laws. Remember the conservation laws that we were looking at says things like the t derivative of u plus the x derivative of f is equal to 0. Now, depending on the problem, f will be related to u in different ways. We're going to first look at an example in which f is equal to v times u, where v is going to be the velocity field or the velocity of some sort of ambient fluid. So in the notes I have a very similar example to what I'm going to talk about here, but let's imagine you have a stream or just some sort of long water like trough going down here. All over college stations we have these drainage dishes. So imagine something like that, but there's no water coming in here or there, it's just water flowing this way. And here is at time x equals 0. And we start with an initial distribution of wood chips, let's say going from point 0, location 0 to location 1. And the arrangement is going to be u of x 0 is equal to x for 0 less than or equal to x less than or equal to 1, and it's going to be 0 everywhere else. And we sort of have the beginning of the string here. So I'm saying wood chips because wood chips, if they are in flowing water, are going to move, okay? But they're not really, I don't really think of them as being a diffusive thing. Like if you just put them in still water, they're not going to spread out in the same way that dye would. They'll just sit there. So that's why I'm using wood chips. Obviously, I'm sort of I'm modeling this as a continuous problem, and wood chips are discrete. So there's some there's some approximations going on. But u of x is the concentration of wood chips. You know, whatever your units are. We could be measuring pounds of wood chips per foot, in which case there are 0 wood chips here, and here there's one pound of wood chips per foot. So u is always going to be a concentration. Whatever the units are going to, you know, whatever the problem is will dictate what the units are. And we're going to assume that the velocity going down this is v of x is equal to 1 plus x. So that at location x, the water is flowing at a speed of 1 plus x units in that direction. So it could be miles per hour, feet per second, whatever the units are. I will let you come up with the units that you want to use. Okay, so then the conservation law is going to be the t derivative of u plus the x derivative of 1 plus xu is equal to 0. Okay, and now what we can do is we can just apply the product rule here, and this becomes the t derivative of u plus 1 plus x times the x derivative of u plus the derivative of 1 plus x, which is 1 times u, equals 0. And so we have the t derivative of u plus 1 plus x times the x derivative of u is equal to minus u. Okay, so I'm going to erase this. So I'm trying to set up the Cauchy problem. So this is the PDE. Now I need to figure out what the gamma curve, the curve, what gamma is and what the data will be there. So if I sketch out my xt plane, so let's say this is x, this is t. Well, we only care about positive values of time because we're starting the experiment at time 0. We only care about positive values of time, and we only care about positive values of x because there's nothing happening over here. So we only care about positive values of x. So we only care about this region here. So then it makes sense that our curve gamma should be the positive x-axis and the positive t-axis. Now, this example corresponds to the first example in this section in the book, and I've set it up a little bit differently. It's going to be very similar, but I just want to do it slightly differently to just show you a different angle on some of these problems. Okay, so we know that at time t equals 0, we're going to have the initial data is going to be x for time, or for a location 0 to 1. That's what this says here, and then 0 afterwards. And well, okay, so we start with 0 chips here. The water is flowing this way. We're only going to have 0 chips. So there's going to be a constant zero concentration of wood chips on the positive t-axis. So U equals 0 there. Okay, so the problem that we get then is going to be the following. We're going to have the t derivative of U plus 1 plus x times the x derivative of U is equal to minus U. And then we're going to have on the positive t-axis, on I'll say positive t-axis, U is equal to 0. On the positive x-axis, U of x 0 is equal to x for 0 less than or equal to x less than or equal to 1, and it's going to be 0 otherwise. Okay, so this is the problem. So our gamma curve is going to be the positive x-axis and the positive t-axis. Okay. Now, we could set this up as we have been doing, but we could say that x prime of s is going to be 1 plus x, t prime of s is going to be 1. We could do all of that. I'm going to show you a different way, simply because I think it's helpful to be able to solve a problem and be able to analyze a problem in multiple ways. But also this sort of thinking is going to be very important for what we do later this week and next week. So the first thing that I want to mention is that a characteristic, the slope of a characteristic, is always the coefficient on the t derivative over the coefficient of the x derivative. We've mentioned this several times before. If you don't understand why, just think of the following, this is why. Our parameterizations are going to be x of s, t of s, and the slope, this is a curve, this is a parameterization. The curve is just going to be t prime of s over x prime of s. Well, t prime is the coefficient on the t derivative and x prime is the coefficient on the x derivative. So this gives t prime of x is equal to 1 over 1 plus x. Okay, so in other words, we can think about our curves as satisfying this sort of differential equation here. Now, it's an easy differential equation because we can just integrate and we get that t of x is equal to some constant plus log of the absolute value of 1 plus x. And we will see in a moment that we don't need to actually worry about the absolute value because we're only going to be dealing with positive values of x. Okay, so typically when we want to, when we write our curves like this, our characteristic curves, we want that c to have information about the point where it crosses the x-axis. Or sorry, not where it crosses the x-axis, where it crosses the curve gamma. So let me begin to kind of draw some a diagram here. So this is the xt plane. So this is the x-axis. This is the t-axis. Black markers really don't work well on this board for some reason. It's annoying. Okay. Now, we know things are going to happen. There's going to be two different sort of places where different things are going to happen. One is going to be at x 0, the characteristic emanating from x equals 0, and one is going to be when x is equal to 1, because we know that along the t-axis, u is 1. We know for x bigger than 1, u is going to be, we know along the t-axis, u is 0. We know on the x-axis, for x bigger than 1, u is 0, and we know it goes from 0 to x here. Okay. So if I think about c equals 0, I have t of x equals log of 1 plus x. When x equals 0, that's t of x is equal to log of 1, so it's going to be 0. So if I take c equals 0, then this function is going to cross the x-axis when x is equal to 0. So we're going to have something like this. I'm going to draw with a dashed purple line. This is t is equal to log of 1 plus x. I only care about this, and x is positive, so 1 plus x is always going to be positive. Okay, now let's think about the characteristic curve that goes through 1 here. Okay, so the curve is going to cross the x-axis when x is equal to 1. In other words, we're going to have 0 is equal to c plus log of 2. We're going to have 0 is equal to c plus log 2. In other words, c is equal to minus log 2. And so here we're going to have t is equal to log of 1 plus x. It's log of 1 plus x minus log of 2, but I can just write this as log of 1 plus x over 2, like that. That's what these characteristics are. Okay, now let's see what happens if I start in a zone up here. If I start in this area right here, the characteristics are always going to be of this form. If t is bigger than log of 1 plus x, so I'm in this region here, it's going to be this logarithmic curve, but we see it's going to cross gamma on the positive t-axis. Okay, so what we're going to have now is, let's see where I can record this information for if t is bigger than the natural log of 1 plus x, then the characteristic is going to be t of x equals, okay, this is t naught, and notice this corresponds to x equals 0, and this over here corresponds to x equals 0, so this would be log of 1, which is 0, so c is just equal to t naught. So t of x is equal to t naught plus log of 1 plus x. So the characteristics, for the points above t equals log of 1 plus x, they're going to lie on characteristics of this form here, where t naught is where it crosses the axis there. Now let's look at what happens. You know what, I'm going to do this in purple. I've got purple here. I'm going to change this to purple. Purple seems to be doing a little bit better with the writing. Anyways, I'll just say it one more time. If a point is above this, is t greater than log. If t is greater than log of 1 plus x, it's going to cross the gamma at the positive t-axis. You know, for this curve, it's crossing at the point t naught. And so t is equal to t naught plus log of 1 plus x. Okay, now, I said something that was, slightly confusing, so I'm editing the video. Hopefully, I've done this before, so hopefully the edit is going to make sense here. But I've just shown that if the point xt is in the zone up here, then we have t is equal to this, and it has this parameterization in s t naught plus log of 1 plus s. This is just using the fact that the graph, if we have, if we're looking at the xy plane and we have y equals f of x, we can always parameterize that as s f of s. That's exactly what we're doing here. Okay, now we're going to look to see what happens if t is less than log of 1 plus x. So that's going to be below this line here. Well, it could be this curve. I could be over here, or I could be over here. I think probably I had something different written over here. I think I probably had t is equal to c plus log of 1 plus x. So now I want to write c in terms of like this crossing point here. X naught there, or it'll be x naught for that one. Okay, now in this case, it crosses gamma on the positive x-axis. That is where t is equal to 0. So we're going to have 0 is equal to c plus log of 1 plus x naught. In other words, c is equal to minus log of 1 plus x naught. And so what we have for these curves in the zone under t equals log of 1 plus x, we're going to have t is equal to log Notice it's log of 1 plus x minus log of 1 plus x naught, but I can just divide by 1 plus x naught. So t equals log of 1 plus x over 1 plus x naught. Okay. So for the curves, the points less than, for the points here, under this dashed curve here, these are going to be the characteristics. And again, a parameterization is going to be s log 1 plus x over 1 plus x naught. And by x here, I mean s. Okay, so there's a parameterization. So notice that we haven't discussed z yet. So we've got parameterizations. For the purple parameterization, x is equal to s, t is equal to that. For the blue parameterizations, x is equal to s, t is equal to that. Z of s is still going to be equal to u along the parameterization. So let's look at the purple parameterization. It's going to be s, comma, t naught log of 1 plus s. Now if I take a derivative, z prime of s is going to be the derivative of that with respect to s, which is 1, times the x derivative of u. I can't write the argument, there's too much room, or there's not enough room. And then plus, this is t naught plus, the derivative of this with respect to s, which is 1 over 1 plus s times the t derivative of u. And we've talked about this before, but the x derivative of u means take the derivative in the first component. The t derivative of u means take the derivative in the second component. Now this isn't the left-hand side of the equation, but notice if I factor out a 1 over 1 plus s, I'm going to write this first, the t derivative of u. And if I factor out a 1 over 1 plus s from this term, it's going to be 1 plus s times the x derivative of u. Okay, and now the thing in the brackets is the left-hand side. So this is going to be equal to minus u, which is z along the characteristics, over 1 plus s. So you get z prime is equal to minus z over 1 plus s. So let me just bring this z prime down. So z prime is equal to minus z over 1 plus s. There's a number of ways that we can think about this. If we divide the z over, we get z prime over z. But z prime over z is just the derivative of log of z. If we anti-differentiate both sides, we get we get log z is equal to c minus log of 1 plus s. X is equal to s, and x is positive, so 1 plus s is positive, so we don't need absolute values. And then if I exponentiate both sides, we get z of s is equal to a over 1 plus s, where a is equal to e to the power of c. Okay, so this is what z of s is. Z of s is equal to a over 1 plus s. All right. And now the initial value, or to determine a, we're going to have to think about what should be an initial value for z. And it'll change depending on whether we're up here or down there. And actually it's going to change on whether, depending on whether we're in this region, or in that region. Okay, so let's think about this. So by the way, I can't remember what I said. If you do z of s along this curve as well, since the derivative of this function is 1 over 1 plus s, you also get that this is equal to z of s. You get the same differential equation for z. Okay, so for t greater than log, of 1 plus x, the characteristic curve is going to be of the form t. It's going to be on a curve of the form t naught plus log of 1 plus x. So a curve like this. And when x is equal to 0, or if we have the parameterized curve like this, when s is equal to 0, this is going to correspond to t naught. So 0, z of 0 is going to correspond to u along the t-axis, which is just 0. Or this is, if you look at this formula, this is a over 1. In other words, a is equal to 0. Okay, so what this is saying, if t is greater than log of 1 plus x, u is equal to 0 here. Oops, I didn't need to erase that. So z of s is equal to a over 1 plus s. And I will let you guys look at similar arguments to show that if t is less than log of 1 plus x over 2, over here u is equal to 0. And so I just now want to talk about the part between these two dashed lines here. So if we have something like, if t is bigger, if you have log of 1 plus x over 2 is less than or equal to t is less than or equal to log of 1 plus x, it's going to cross the x-axis. That is going to cross the curve gamma when s is equal to x naught. Then we're going to have 1 plus x naught over 1 plus x naught, that's 1. And so this component is going to be equal to 0. So in this case, we know that z of x naught, that's where it crosses the x-axis. Well, that's going to be u of x naught, or u of x naught 0. That's just going to be equal to x naught. So z of x naught is equal to x naught. And this is equal to a over 1 plus x naught. So we're not looking at an initial condition when s is equal to 0. We're looking at a so-called initial condition when s is equal to x naught. Okay, and so now this says that a is equal to x naught times 1 plus x naught. Okay, so now what this says is for the curves, for the points, I mean between these 2 points here, z of s is going to be equal to x naught times 1 plus x naught over 1 plus s. Okay, now we need to figure out what x naught and s are in terms of x and t. So let's do that now. So if I look at my parameterization, it says x is equal to s, and it says t is equal to log of 1 plus s, but x is equal to s. So I'm going to write this as log of 1 plus x over 1 plus x naught. And now what I want to do is I want to solve this for x naught. So if I exponentiate both sides, well, so if I exponentiate both sides, I'm going to have e to the t is equal to 1 plus x over 1 plus x naught. If I multiply both sides by 1 plus x naught, and divide by e to the t, I'm going to have 1 plus x naught equals e to the minus t, 1 plus x. And then again, I want x naught, so I'm going to subtract 1 from both sides, and I've got x naught is equal to e to the minus t, 1 plus x minus 1. Okay, so now what this says for this, I'm going to have to erase it. Well, there's too much stuff here. So this is what x naught is. Let me just record this here. X naught is equal to e to the minus t, 1 plus x minus 1. Okay. All right, so now u, for the values of x, for the points xt that satisfy this inequality, u of xt is going to be equal to x naught, which is this, e to the minus t, 1 plus x minus 1, times 1 plus x naught, which is e to the minus t 1 plus x divided by 1 plus s, which x, remember, s is equal to x, so notice those 1 plus x's cancel. And remember, we only care about positive values of x, so there's no ambiguity. Okay. So then what this tells us is u of xt, u of xt is equal to this, e to the minus t 1 plus x minus 1 e to the minus t for x and t values satisfying that inequality. It actually turns out we can write this inequality a little bit easier. This inequality a little bit easier, a way that makes a little more sense and is more consistent with how we have things there. So this is minus t. Notice if I look at this inequality here, for example, and I raise that to I raise e to the power of that, I'm going to have 1 plus x over 2 is less than e to the t. Or I could say, okay, I can multiply both sides by 2, divide both sides by e to the t, and we've got e to the minus t 1 plus x is less than 2. Okay, and then this inequality here would be e to the minus t 1 plus x is greater than 1. Okay, so I'm going to go back to purple now. Sorry, I'm just going to rewrite this, but write it in purple now. So now what we've got is u of xt is equal to this, e to the minus t 1 plus x minus 1 e to the minus t. Okay, and this is going to be when 1 is less than e to the minus t 1 plus x is less than 2, and it's going to be 0 otherwise. Okay, so this is 1 less than e to the minus t times 1 plus x is less than 2, and 0 otherwise. Okay, and I'll explain why in the next video, why I wanted to write the inequality this way rather than this way, and the reason, well, you'll see why in the next video. Okay, but that's it. This was an alternative method for finding for solving this differential equation. We're going to use similar ideas pretty critically when we look at quasi-linear equations. But that is it for this already very long video.